Today we're going to look at applications of trigonometry. The learning goals that we have for today are we're going to solve problems involving angles of depression and elevation, and also solve problems involving bearings. So angles of depression and elevation. The angle of elevation is measured up from the horizontal. So in our diagram here, the angle of elevation is this one here, and it's measured up from the horizontal. So horizontal up to the point that we care about. So if this was a building or something like that, then the angle of elevation from this point to the top of the building is this one here that relates to the horizontal point. The angle of depression is measured from the horizontal down. So if we're looking from the top of the building and we're asked to find the angle of depression to this point down here, then we once again look at the horizontal along here, but we look downward. So the angle of depression looks downward. So these two angles are identical, and they're identical due to the alternate angles in parallel lines. So these two horizontals are parallel, and that means the angles of elevation and depression are equal. They're going to be the same. It's the Z rule from a couple of years ago. So whenever we're given a problem that we can solve using trigonometry, it's going to be something in real world. There's going to be angles of elevation or depression involved. There's going to be real distances that we need to find or angles that we need to find. So in order to do that, we need to draw a diagram and label key information on that diagram. We need to identify and draw the right angle triangle separately so that it's very clear exactly what we're trying to solve. We need to then use our trigonometric rules or Pythagoras or whatever relationships that we understand to be able to find the unknown side or angle, and then we need to express our answer in a sentence that relates to the question that's been asked. So let's have a look at our first example here. We've got a helicopter. It's hovering at an altitude of 250 meters. Angle of elevation from the helipad to the helicopter is 35 degrees. Find the horizontal distance of the helicopter from the helipad to the nearest centimeter. So if we have our helicopter whizzing above the ground, helicopter, it is going to be 250 meters up from the ground. That's our altitude, and it is at a certain angle of elevation from the helipad. So the helipad's over here, H for helipad, and we've got our line of sight from the helipad to the helicopter. The angle of elevation is from the horizontal, so that means our angle of elevation is here. We're being asked to find the distance of the helicopter from the helipad, the horizontal distance. So this is what we're trying to find here, this side here. So you'll notice that it actually makes a right angled triangle with our the altitude going straight up, horizontal distance straight across. So we need to redraw this triangle. This is the first thing. We've drawn a diagram to show the situation, labelled it, and all of the parts on it, but now we need to draw a triangle so it's very clear what we're actually trying to find. So we'll draw our triangle here. Doesn't need to be to scale or accurate, but we need to just label now the very pertinent information. So 25 degrees, X is what we're trying to find, and this side here is 250 meters. So now we can try and use trigonometry to solve our problem. We have got our opposite side to the angle, and we've got our adjacent side to the angle. So because we've got the opposite and adjacent, that means we need to use our tan relationship. So tan theta is equal to opposite over adjacent. So our angle is 25 degrees, opposite side is 250, and our adjacent is x, what we're trying to find. Multiply both sides by x, we get x tan 25 is equal to 250, and x is going to be equal to then 250 divided by tan 25. If I divide both sides by tan 25, that means I get for x 357.04 meters. It's asked me to answer to the nearest centimetre. So the nearest centimetre is 2 decimal places in metres. So 354 metres and 357 metres and 4 centimetres. So I've answered to the nearest centimetre now, but I need to answer in a sentence. We can say, therefore, the horizontal distance of helicopter to helipad is 357.04 metres. Looking at example 2 now. We've got 2 vertical buildings 57 metres apart, and they are 158 metres and 237 metres high respectively. That means that the first one's 158 metres, the second one is 237 metres. Find the angle of elevation from the top of the shorter building to the top of the taller building, correct to 2 decimal places. So if we're actually having a look, and drawing a diagram now, we've got our shorter building, have our taller building, and we care about, or we can draw the distance between them is 57 metres is the distance between them. The first one is 158 metres high, 158 metres high, and the second one here is 237 metres high. We are trying to find the angle of elevation from the top of the shorter building here to the top of the taller building. So here we're trying to find this angle of elevation here, theta. So now we can try and think about, if we've got our, trying to find the height difference here. The height difference from the top of the buildings is going to be 79 metres from doing the 237 metres minus 158. So we probably need to record that and write down the height difference. It's going to be 237 minus 158, which is going to be 79 metres. We can draw our diagram now of our triangle. So we've got all the information we need. We're trying to find angle theta. We've got that the horizontal distance between the 2 buildings is 57 metres and the vertical distance is 79 metres. For our triangle here, the relationship that we have, we've got the angle that's opposite, or the side that's opposite the angle that we care about, and the side that is adjacent to the angle that we care about. So we know that we need to use the tangent trigonometric function. Tan theta is going to be equal to opposite over adjacent. 57 over 79. So that means theta is going to be equal to the inverse tangent of 57 over 79. And then if we get that, put that into our calculator to 2 decimal places, which is what we're asked about, 2 decimal places, we get 54.19 degrees. And then we need to answer in a sentence, the final thing. So we can say then, therefore, the angle of elevation from the top of the shorter to the top of the taller building is 54.19 degrees. Looking now at bearings. Bearings are used to communicate direction. They're important in navigation for ships, pilots and military applications in particular. We often talk about true bearings. True bearings are measured from north, from true north here, or from due north. So that's pointing straight up in this diagram at the right here. And they're measured clockwise. So we can see here these true bearings. We go 45 degrees and then keep going around 90, 135, 180, 225, 270, 315 and 360 all the way back to the start. Okay, so 360 degrees and 0 degrees are both directly north. True bearings are written using 3 digits, always 3 digits, followed by degrees T, which stands for degrees true. Next year you'll look at using other ways of describing bearings, but we're going to just focus on looking at degrees true this year. So, sorry, true bearings this year. So if I was to say 135 degrees true, that's going to be in this direction here. So let's look at an example now. Once again, we draw a diagram, we isolate the triangles and try and find our solution. So we've got a ship travelling due south for 5 kilometres, then on a true bearing of 120 degrees for 11 kilometres. So let's draw this as a diagram. So we're going here 5 kilometres due south, and then a true bearing of 120 degrees. 90 degrees would be just straight out east, but we're going slightly more than that by 30 degrees. So we're going down about this angle, maybe a little bit more, for 11 kilometres. So we can just split up our plane here into what we know as right angle. There's a right angle here, and then this angle here is going to be 30 degrees more, because this is going to help us when we're writing and finding our solutions for part A and part B. So for part A, we're asked how far east the ship is from its starting point, corrected 2 decimal places. Well, we have a triangle that we can use to work this out. East is going to be going out in this direction here. We want to know how far east it is. So we want to know what this value is, x. We know that when we've been moving east, it's been the second part of the journey, when we're going on our true bearing of 120 degrees for 11 kilometres. So we know that this side here is going to be 11 kilometres long of a triangle, and it's going to make a right angle triangle if we drop a line straight down, because it's going to be travelling a little bit east and a little bit south. So we also know that this angle here for our triangle is going to be 30 degrees. And we know that because it's gone 90 degrees to go east, and then a further 30 degrees to make up the 120 degrees true. So now we have our triangle, we can solve this problem. We have got the adjacent side to our triangle, and we've got the hypotenuse. So because of the adjacent side and hypotenuse, we've got the cosine relationship, the cosine trigonometric function, cos theta equals adjacent over hypotenuse. So it's going to be cos of 30 degrees is equal to the adjacent side x divided by our hypotenuse 11. So that means if we multiply both sides by 11, we get that x is equal to 11 kilometres times cos 30. So that means we're going to be, or the value of x is going to be 9.53 kilometres east of its initial position. So we can answer the question then. Therefore, the ship will be 9.53 kilometres east of original position. For our part B, we need to use our same triangle. Remember, we've gone down by 5 kilometres, and then we've gone at an angle of 30 degrees here to the east, and then we've gone down a little bit more because of that, 11 kilometres, because we've gone at that 30 degree angle. So we've gone a total south of the 5 kilometres we travelled south to start with, plus whatever this value is here, this y value of going down further south by a small amount. So what we can do is we can find this value y and then add the 5 kilometres onto it to figure out how far south we are from our original position. So remember, drawing our triangle again, 30 degrees, because we've been travelling at that 120 degree true bearing. We know this is 11 kilometres, And our relationship now is we've got the opposite side now and the hypotenuse. So we need to use our sine relationship. So this is sine theta will be opposite over hypotenuse. So that means sine of 30 degrees is going to be equal to y over 11. Y will therefore be equal to 11 sine 30, because we multiply both sides by 11, and we'll get that this is 5.5 kilometres. Now we're not finished yet, because that only tells us how far south we went in the second part. So we initially travelled 5 kilometres south, and then we've travelled a further 5.5 kilometres south. So that means we can say total distance south is going to be equal to 5 plus the 5.5, which is 10.5 kilometres. So we can say, therefore, ship will be 10.5 kilometres south of its original position. So just recapping our learning goals for today, we've learnt how to solve applications questions using trigonometry, and also being able to use and solve problems that involve bearings as well.